a question came up about resonances. Why don't we talk about resonances? Well, I wanted to mention also, why are we modeling infinite plate? There's no such thing as an infinite plate, right? Plates are finite in shape. Do you remember? I mentioned the reason before. You don't remember? Okay. If instead of an infinite plate, if you have a finite plate, okay, and somehow you're exciting it, it vibrates, and it radiates. Now the radiation is not as simple as in the case of infinite plates. The reason is radiation from here, okay, refracts to the other side and back and forth. And modeling these ends is very complicated. But it is something that we will get to a little later. Secondly, any vibration now is expressed in terms of Fourier series. Okay? Now you have mode shapes. And mode shapes, depending on the boundary conditions, first mode, second mode, and so on. You're only considering these. And if you look at, let's say, a rectangular plate, let's see, 1, 2, 3. Okay, this is, let's say, 3-6 mode. Okay, and if you look at a cross section, maybe it is like this in that way and so on. So at a given moment, the middle parts will act almost like the way an infinite plate would act, but the edges, they don't interact. There's nothing to interact on the other side. So the modeling of these will have to have special conditions, and we will talk about it hopefully a little later. That's when you have resonances, etc., and that we have not talked about except for spatial resonance. Okay. Boundary conditions become important, of course, both acoustically and as well as vibration, for vibration purposes. Okay, with that, let's talk about radiation in spherical coordinates. As I mentioned in the very first class, the way we select the coordinate system depends on the shape of either the acoustic field or the shape of the sound source. Okay? For plates, we use Cartesian coordinates, but not everything is flat. Certainly not everything is infinite. Some things are either cylindrical in shape, like pipes. Okay, radiation from a pipe, you'd use cylindrical coordinates, or they have the shape of a spherical geometry. Now, again, depending on the frequencies, sometimes, let's say you have either an engine or a pump of some sort that has a funny shape. It doesn't fit into any particular coordinates, okay? But at very low frequencies, for instance, this actually can act like a spherical source. So we can model it at low frequencies as a sphere and look at the vibration, look at the radiation in all different directions. So then we will, after maybe a couple of lectures, we will go down to simplifications about how you model simple systems as a monopoles, meaning something like a balloon, okay, that vibrates in and out, or a dipole, okay, one side, there are two monopoles that are out of phase, etc. And but just for some mathematical rigor, okay, we'll start with the most complicated, and then we'll simplify it. Most complicated meaning, we'll take the spherical radiation equations, we'll go through the separation of variables, where you'll learn Legendre, you probably know these, but Legendre functions, Bessel functions, and so on, Hankel functions, okay? You know these? Yes, no? You've heard the names at least, okay? And then use very low order cases as examples. So with that, let me begin with the radiation from spheres. Okay, and the starting point is the wave equation. And of course, wave equation, the Laplacian describes the spatial component on the left and the time variation on the right. Now, the Laplacian in explicit terms, okay, this is where one can make errors. Okay, let's make sure we're okay. All right. I need to get you a figure on this. Okay. Careful here, this is phi. Okay, the others are theta. I'll draw a figure later to describe each one of these. Now we want to simplify this by substituting eta as cosine theta. So sine theta will be square root of 1 minus eta square. Okay. Okay. Now we'll use the usual solution, separation of variables. Okay. We're able to separate into 4 different components, 3 in spatial coordinates and time. If we substitute all these and simplify, we use this. So K here is omega over C. You can simplify this equation just combining these. And we set this to a constant since it depends. Yes. And we also set 1 over phi. Yeah. Okay, we set these values. Substitute back. Then we have C minus we rewrite them. All right. So we have 1, 2, 3 equations, differential equations in space. And we want to be able to solve these. You're familiar with these, right? You have seen them before somewhere. Okay, now, solutions. Of course, the first one is fairly obvious. We're writing the general solution, so it would have an amplitude n. Note now this n here, okay? N here couples it to the other angle, Okay, and you'll see that through C it couples to this. Okay, so this is AN cosine and phi plus BN sine and phi. Now, it's fine, it's obvious, but there are two conditions that you must remember. Phi is a variable between 0 and 2 pi, and for continuity, this must be an integer. Okay, n must be an integer. That is of consequence because n appears in the other solution. Okay. Now, if there is axial symmetry, okay, if this is a sphere and around its axis there's a symmetry, then n is 0 because there's no variation around the angle. Okay. And when n is 0, this will simplify, and so on. Okay, now let's, we have these. Actually, let's do this. Let's solve the the third set of equations. Legendre polynomials. Okay, now let's note that eta is same as cosine theta. That means its values range between -1 and 1, because that by definition, okay? So that's that. Okay, so, and C constant, true for all values of eta. So first of all, let's see for the symmetric case, axisymmetric case, we can rewrite the equation. And if we set P, the solution, to an arbitrary polynomial, A0, A1, eta, A2, eta squared, and so on. Just an arbitrary polynomial. Then we can similarly determine its first and second derivatives, A1, 2, and then the second one. Okay. Now, substituting these back into this equation, okay, we want to get some values for them. Leave it there. This, I guess. Okay, substituting back here, then we will get expressions that show a relationship between these coefficients. And then you substitute it back in here. You have C over 2. What we're trying to demonstrate here is that a solution, you know, when you see an expression like this. Let me just have you just a moment. When you see an expression like this, you know immediately what the solution looks like. What we're trying to demonstrate here is that when you have an equation like this, okay, if you write the solution as an arbitrary power series and then substitute it back, what you then see is there's a relationship of recurrence. Okay, higher coefficients can be expressed in terms of the first one or two, okay? And when you do that, now you're getting a solution that's more manageable. P, yes. Substituting then back into this, the pressure, sorry, not pressure, but the function, Legendre function, we can write it in terms of A0 and A1. Because everything now can be expressed in terms of two coefficients. Okay, once again, I don't want to make too much of a case here, but you can see here the unknowns, coefficients A and B, which we're going to find out from various boundary conditions. You can see here the unknowns, just 1 and 2, okay? Because we were able to write all the higher coefficients in terms of A0 and A1. You can do this and you can demonstrate that. Okay, so we have this, and C, of course, is part of the equation, and so that's that gives another relationship to us. So, okay. When these two series are infinite, they diverge at eta plus minus 1. Okay, remember they are valid up to plus minus 1, the range of validity, because eta is cosine theta. Okay. Now, because physically pressure solutions cannot be or must be finite, must have finite amplitudes is better, must have finite amplitudes. One should vanish. And the other breaks at a finite number. i.e. C equals 0 or 6 or 20, etc. And this gives us A1 and C. Okay. So the bottom line then is, I want to leave that there. The allowed values we have are constant. C is m times m plus 1. And m can change from 0, 1 to integer values. So the solution then is, the solution is obtained by substituting for C in the equation of motion, in the wave equation. In this equation. Okay, here, just very briefly, if I can have 10 seconds of your time, just very briefly. What we're saying here is that, fine, this is a series, but this series will diverge at plus or minus 1 values of eta. And so in order to be able to make this realistic, okay, we need to put a condition. And that condition comes by assuming that pressure cannot be infinite physically, and that gives us, or that helps us impose a value for C, the allowed values for C. And these are C, okay, integer values. And then you come back and put those in here, then you have an expression for P, the Legendre function. That's the process that we have followed. And when you do that, examples, m is equal to 0. Yes, of course, C will be 0, and the solution then one. That means completely symmetric. If m is equal to 1, C will be equal to 2, then and so on. So the general solution for the Legendre equation is okay. Certain properties you remember trigonometric functions have certain properties. Sine square theta plus cosine square theta is equal to 1. That's a property. as an analogy, Legendre functions also have certain properties, and they are very similar to the properties of Bessel functions. Okay, once again, recurrence. Let me just write a couple of them down. And the other here is maybe one last one. All right. What this last condition shows, what would you call that? Do you remember? What is that condition refer to? The last one. What does it say? Why don't you finish writing and then let's talk about that last equation. Finish writing, everybody? Not yet? Okay. Who can read this? Just read it. See what it says. Read it aloud. Yeah. What does it say? What's capital P? That's Legendre function. Okay. What does it do? Can you read it? John, why don't you read it? What do you read there? On the left-hand side.
PS eta times EM eta integrated from -1 to 1.
Okay. Okay. What does that say then? What's P? What's PS and what's PM?
Legendre polynomial order S and M.
Exactly. Okay, and you're integrating it from -1 to 1 because they're valid between -1 and 1. So the entire range of their validity. Okay, and what does the right-hand side say? You're good at this, so continue.
If their orders are equal, the integration is 0.
If their orders are unequal, yes. So only when S and M, their orders are equal, it has a value, otherwise it's 0. And what is that condition called? What is this called then? Exactly. Orthogonality. So Legendre functions are orthogonal. Well, have you heard orthogonality before? No? Yes, maybe. What else is orthogonal? What other functions do you remember that are orthogonal.
In general, they want orthogonal basis functions, like in Fourier transform.
Yes, sine, cosine functions are orthogonal functions. Yes, if you have sine n pi x multiplied by sine m pi x and integrated with respect to x from, let's say, minus pi to plus pi, you'll have a very similar result. So what is the property of orthogonal functions? It's a very important tool. We use them to represent arbitrary functions by expanding them. Okay, just like Fourier series with Fourier trigonometric functions, exponential functions, etc. So next time we come back, we'll be able to. Sorry, what this then will enable us to do is, if we have a radiation pattern that's different, in theta, one direction it's high, next to it it's low, all funny shaped, we'll be able to express it in terms of Legendre functions. If it is completely, let's say, symmetric, the result is going to come out to be finite only for SM0, and so on. Okay? And you'll find Bessel functions to be the same, and other functions similar to this. As long as they're orthogonal, then you're able to express an arbitrary function in that variable with these functions. Any questions? This is a different approach to things. Don't let it get you scared. But I think these are good tools to have. And when we start solving them, we will use, of course, the first several modes. Others can really be done effectively using numerical methods. Any questions on these? Okay. Thank you. See you next time.